Okay, coming to the definition of stochastic independence, it goes like this. Actually, it is for continuous random variables, but a generalized definition is being given in Gupta and Kapoor. What that is let us consider two random variables, capital X and capital Y. Actually, here it's been given both for discrete and continuous, but you will see in course of time while handling problems, you will see that it's actually the definition for continuous random variables. They can be discrete or continuous. When I say that with PDF or PMF. Okay, what is PDF? Probability density function or probability mass function. It can be anything, respectively actually. Why? Because density function is for discrete, mass function is for continuous. Okay. PDF or PMF, it's given by F capital X, Y, X comma Y. And the marginal probability distribution functions are given to be probability density functions or mass functions, marginal probability mass functions or density functions are given to be Fx and Fy. I can also say Gy, guys, here. Usually he is using this notation Gy in Gupta and Kapoor. Respectively, we have something called compound probability theorem. Compound probability theorem. Compound probability theorem. What that says is, or the conditional probability, guys. What that is Fxy x comma y. This is equal to F capital X, okay, G y by x. Okay, yeah. Okay, what that is there where G capital Y by capital X is the conditional probability distribution function of Y, because X is in the denominator, of Y for given value of X. Given value X is equal to X. Okay, yeah. So let's see how actually they are saying this thing, this terminology, how they are using the words like stochastic independence and all. I will just show, which is very simple actually. Okay. What that is, see, stochastic independence. I should talk about stochastic independence here, right? So if G of Y by X, I mean, of course, in the suffix, there is capital Y and capital X as well. Does not depend on X. Does not depend on X. As I made a mention in the previous video, it is like your mutually exclusive events. Depend on G of Y by X, does not depend on X. Then just see, then the marginal PDF, marginal probability distribution function is of G is given by what that is G of Y. This is equal to integral minus infinity to plus infinity f of x comma y dx. Okay, now I have defined it. What that is minus infinity to plus infinity. I've already written that compound probability theorem. I have already written in the previous case, or the conditional probability kind. Dx, this is okay. Yeah. Now you see here, G y by x is independent. So if I take it out, it doesn't depend on x. So if I take it out, G capital Y by x, Y by capital X, Y by x, minus infinity to plus infinity, F capital X dx. If I take, why I have taken it out? Because since G Y by x is independent of x, is not dependent on x. I'm integrating with respect to x now, and it is not dependent on x, so I can take it out like a constant, right? Yeah. So what happens? Just see this value. This value turns out to be 1. G y by x, y by x into this value turns out to be 1, because sum of all marginal probabilities of x would be 1. Similarly, sum of all marginal probabilities of y also would be 1, right? We have seen more clearly in discrete case when we have constructed the joint probability distribution table. Okay, so clearly I can see g of y is equal to this value when, I'll just write here, when g y by x is independent of x, This is nothing but your stochastic independence, guys. And then I have done it using integration. And once integration is there, it is for continuous random variables. Though the definition goes for both discrete and continuous, stochastic independence is specifically for continuous random variables. Okay, so I'll define independent random variables first. Okay. Independent random variables. I mean the stochastic independence only in a different version. What that is the two random variables, capital X and capital Y, with they have a joint probability distribution with a joint PDF, probability distribution function, or PMF, whatever. PDF is probability distribution function. Distribution can be density or mass. Okay. Distribution function f capital X, Y, X comma Y, and marginal PDFs fx and gy respectively, because I am saying for x it is x, it is y, it is y, respectively, are said to be, please remember this, are said to be stochastically independent, are said to be stochastically independent. When you can say that, just see here, that compound probability theorem only, I am rewriting it. When I can write x and y terms separately, that's it. Okay. Like your mutually exclusive events where P of A intersection B, I'll write it as P of A into P of B. Otherwise, what it would have been, if they are not mutually exclusive, it would have been P of A into P of B by A, from which the conditional probability also pops up. Okay. This is for a single variable. Now here I'm talking about two random variables, which are interdependent because I have a joint probability distribution function for both of them. Okay. This is the definition for stochastic independence, guys. Usually definitions can be asked. This definition is favorite for the examiner. So do check the definition. Okay. I can just do problems in the next video. I shall show you 1 or 2 problems in the next video.